Practice motion problems answers PowerPoint. First problem is a plane accelerates from rest to a speed of 65 meters per second, 10 seconds. Determine the acceleration. The motion equation we're going to use is a is equal to v sub f minus v sub I over t. Plugging in our numbers, we get 65 meters per second minus 0 over 10 seconds, which our calculator tells us will be 6.5 meters per second squared. Second problem involves a car accelerating from rest. We want the final velocity and distance traveled. To get the final velocity, since it's from rest, the initial velocity is 0. There's the acceleration, there's the time. These quantities are related by v sub f is equal to v sub I plus at. Plugging the values in, the answer turns out to be 15 meters per second. Second thing we want is the distance traveled. Quantities are related by v sub it plus 1/2 at squared. Inserting the values. First term, 0 times anything is 0, so that goes away. Square the 6 to get 36. And then after multiplying, you get 45 meters. The second squared here and here cancel themselves out. Problem number 3 involves a dragster. They give us the speed in miles per hour. We need to convert this speed to meters per second. So we need a conversion factor. Physics book gave me this. Okay, so we're going to set it up in our factor label method type system. Cancel out the miles per hour, put them on the bottom, meters per second is therefore on top. After cancellation and a little calculator work, we get a final velocity of 143 meters per second. We will then use this relationship, since we know the quantity is v sub I, distance, time, and the final velocity. We're going to put the 0 in right away because that often makes calculations easier, as it will in this case. So I'm just going to put it in. The numerator then becomes just v sub f over 2 multiplied by t. Taking this onto a new page, and then we need to solve this equation for t. And the way we can do that is multiply each side by 2. That will eliminate that 2 cancellation. What we're left with is 2d is equal to vf times t. Divide each side by v sub f. And after canceling, we get t is equal to 2d over f. Putting our numbers in, the meters here cancel out, and you could kind of do a little algebra with your things here. This seconds actually ends up coming up on back on top. If it's in the denominator of the denominator, in the denominator of meters per second, and it's in the denominator of the quantity, you can prove algebraically that it will come back on top, and so your unit will work out to be seconds. And the number is 5.59. Number 4 involves a boat accelerating, and we want that quantity of that acceleration. Given v sub I, v sub f, d, and a, we want to use this expression. And we want to solve this expression for a. So since we have a term here, v sub I squared, and a term here, 2ab, we need to isolate the second term. In other words, we need to get rid of the vi squared from the right-hand side. We can do that by subtracting it. From the right-hand side, it's canceled out. The left-hand side becomes v sub f squared minus v sub I squared is equal to the 2 times a times b. We want to solve for a, so we need to get rid of the 2 and the d, and we can do that by dividing by the 2 and the d, both sides. Over on the right-hand side, the 2's and the d's cancel out. We're left with a is equal to v sub f minus v sub I squared over 2d. Now we plug our numbers in. The numerator becomes 2,700 meters squared per second squared. Denominator becomes 200. This meter in the denominator will cancel out one of those, and we'll be left with meters per second squared. And the number turned out to be 13.5 meters per second squared. So number 5 involves a motorcycle accelerating from rest. We want the final velocity. These quantities are related by expression. Put the numbers in. 2 times 12.5 times 50 is 1,250. Meters times meters is meters squared over second squared is equal to v sub f squared. To get v sub f, take the square root of both sides. The square root of 1,250 is 35.4, and the square root of meters squared over second squared is meters per second. Number 6 involves a rock being dropped from a bridge. So it's a vertical problem, so it involves the acceleration of gravity g. It's dropped from rest for 3 seconds. And we want to know how high is the bridge over the river. So how far will the rock be displaced from top to bottom? These quantities are related by this expression. The first, v sub I being 0 will make the whole first term 0, and 1/2 g times v squared. Don't forget to square that last term, and the answer turns out, or the displacement is negative 44 meters, so the bridge is 44 meters high. Number 7 involves a stone dropped from a cliff. How long does it take the stone to strike the plane? It's displacing 54 meters in the negative direction. These quantities are related by v is equal to vi equals 1/2 g squared. You need to solve this for the time. Well, the initial velocity being 0 will mean that the whole first term is 0, and so it goes away, and so we're just left with v is equal to 1/2 g squared. We're going to solve this for t by first multiplying by 2. That will get rid of the 1/2, because 2 times 1/2 is just 1, and so this right-hand side becomes just gp squared is equal to 2v. We then divide out g, and we're left with t squared is equal to 2v over g. Starting on a new page, we then take the square root of both sides. Now we plug our numbers in. Notice that the negative signs cancel themselves out. They have to, because you can't take the square root of the negative number, so they must cancel out. The meters also cancel out. And as discussed before, if it's in the denominator of the denominator, then it comes back on top. And after you square root it, it becomes just seconds. And then the calculator, 2 times 54 is 108, divided by 9.8 is some number I'm not sure, and take the square root of that and get 3.32 seconds. Number 8, baseball is hit straight up with a velocity of 25 meters per second. And how long does the ball remain in the air? So we have an initial velocity of positive 25 meters per second. We always have g, and we're looking for time. We need one more known, okay? And we're going to get that by doing a little trick. We're going to consider only the first half of the flight, because for the first half, just on the way up, the final velocity is 0. That will give us that last known that we need. So here's our data table now. V sub I is positive 25 meters per second, V sub f is 0, g, and we want t, which is related. These quantities are related by V sub f is equal to V sub I plus gt. V sub f is 0. We want to find t. We want to isolate the t, so we can do that and get it by itself by subtracting off the vi from each side, just to get this term alone. Right now there's two terms here, V sub I. Going back a little bit, there's two terms over here. We need to isolate the second term. We need to get rid of this. We can do that by subtracting it out. And then we get negative V sub I is equal to gt. And then we can isolate the t itself by dividing out the g. So we'll be left with t is equal to negative V sub I over g. Plugging in our values, negative, this negative comes from here, and then V sub I is 25, and then G is negative 9.8. A whole lot of stuff cancels out. The negative signs cancel out, the meters cancel out, They are both in the numerators. This meter is in the numerator of the numerator. This meter is in the numerator of the denominator. They cancel out. This second is in the denominator of the numerator. This second squared is in the denominator of the denominator. So, though second squared, one of those will cancel out this second. The only thing left is second, which is in the denominator of the denominator, so it comes back on top. And then 25 divided by 9.8 is 2.55. This is only the time for the first half of the flight, however. Remember that little trick that we did? To get the total amount of time that the ball is in the air, we need to multiply this by 2. 2.55 seconds up, 2.55 seconds down. To get a total flight time of 5.10 seconds. Second question is, how high does the ball rise? Again, we're going to consider only the first half of the flight, since that's the only time that the ball is rising. We want the vertical displacement. Here's our data table. Initial velocity positive 25. Again, the final velocity is 0. There's g, and g is what we want. These quantities are related by, we need to solve this for d. Put in the 0, and we need to isolate the d, which is embedded in this term, and there's also this over here. So once again, we need to take this over to the other side to isolate this term. These subtract off, and you get this. Negative d sub I squared is equal to 2gd. Now, we need to eliminate the 2 and g. So divide each side by 2 and g. 2's cancel out, g's cancel out, and d is equal to negative d sub I squared over 2g. Plugging our numbers in, negative, this negative comes from the algebra, and then d sub I is 25. Don't forget to square it. Divided by 2 times g. The negative signs here cancel themselves out, so we're left with a positive displacement, which makes sense because the ball's going up. After a lot of canceling, we're only left with meters this time. And the calculator says an answer of 31.9. Number 9 involves an air pressure rocket, stayed in the air 6.8 seconds. We want the initial velocity. Again, we're going to consider only the first half of the flight. That gives us this df is equal to 0 quantity. We're looking for the initial velocity. We know g. Now, since we have a time of 6.8 seconds, but if we're considering only the first half of the flight, we need to take only half of this time. 6.8 seconds was up and down. We have to cut this total time in half. So the time from the ground to the highest point is half of 6.8 or 3.4 seconds. And that's the quantity that we use today. These are related by this function, or this equation. V sub f is v sub I plus gt. We want to solve this for v sub I. First, we'll put in the 0, and then we'll isolate the v sub I. We need to separate it from the gt. We can do that a couple different ways, actually. We could subtract off the gt, or we'll just subtract off the v sub I. Doesn't really matter. We'll subtract off the vi. That'll take it over to the left-hand side. And we'll be left with negative v sub I is equal to gt. Go ahead and plug in your numbers now for g and for t. And you'll get negative 33 meters per second. The seconds and one of the seconds down there cancel, in meters per second. And multiply each side by negative 1, and you'll get v sub I is equal to 33 meters per second. The last one involves an arrow being shot straight up with an initial velocity of 45 meters per second. How high does it rise? So we want vertical displacement. G, we need got one more known, so of course we're going to consider only half the flight, where v sub f is equal to 0. Which actually makes sense because we want how high it goes, so we're really only interested in the first half of the flight. These four quantities are related by this function, which we're going to solve for d. There's a 0, so of course we're going to insert that. We're going to isolate this term, subtracting the first one from each side. You get negative v sub I squared is equal to 2 times g times d. Divide each side by the 2 and the g. And we get d equal to negative v sub I squared over 2g. Plug your stuff in, that value's in, negative sign, and then v sub I, don't forget the square, 2g. Negative signs cancel themselves out, and my calculator gave me an answer of 103.